Hello, abstract algebra students. We will now explore the various algebraic structures on P of M. So the power set P of M is our set. We have our familiar notion of set equality from foundations. And then we have three operations, intersection and union, which are familiar from foundations, and symmetric difference, which is new. I am going to talk about symmetric difference in this lecture, and then you can talk about intersection and union on the homework. Okay, so as it turns out, P of M is an abelian semigroup under both intersection and union and under symmetric difference. So all four of the properties, commutative, associative, well-defined, and closed, hold for all three of these operations. I will prove that now for symmetric difference, and I will start with the commutative property. So the claim that I want to prove is that symmetric difference is commutative on P of M. Now, let's first think about what we want to show here. Let's apply the definition of commutative to the set P of M and the operation symmetric difference. So first we think, what does it mean if we're in P of M? It means we're subsets of M, so we're sets. So we should use capital letters for our A and B. For all A, B in P of M, now the operation is going to be symmetric difference. So I want to show that asymmetric difference B equals B symmetric difference A. Now, this is a quantified if-then statement. So we have a for all quantifier. So that means we need to begin by letting AB in P of M be given. Now think about what A and B are. They're members of P of M, so they are subsets of the set M, so they are sets. So this equation, asymmetric difference B equals B symmetric difference A, is a set theoretic identity, which means from foundations, the easiest way to prove it is using truth tables. So let's consider the following truth table. And let's make a table here. We have got X is a member of A and X is a member of B as our two independent propositions. And we are going to need, therefore, 4 rows plus the heading. And we are going to need 4 columns. For X is a member of A, X is a member of B, X is a member of A triangle B, and X is a member of B triangle A. So our truth table is going to look like X is a member of A, X is a member of B, X is a member of A symmetric difference B, and X is a member of B symmetric difference A. Now, these first 2 columns, for X being a member of A and X being a member of B, these are our independent propositions. So Just like we've always done in foundations, the first column is true, true, false, false. The second of the independent column is true, false, true, false. This gives every combination of trues and falses for our propositions x is in A and x is in B. Now, remember that the symmetric difference is the set theoretic analog of the exclusive OR. We return true when exactly one of these two statements is true. We return false when either both are true or both are false. So here we have true symmetric difference true is false. We have true symmetric difference false is true. We have false symmetric difference true is true. And we have false symmetric difference false. So false exclusive or false is false because it's not the case that exactly one of them is true. Now we do the same thing for B symmetric difference A. True exclusive or true is false. False exclusive or true is true. True exclusive or false is true because exactly one of them is true. False exclusive or false is false because none of them are true. So now we look at our truth tables. They match, these guys match, this row matches, this row matches, this row matches. Therefore, x is in asymmetric difference B is logically equivalent to x is in B symmetric difference A. So the truth table shows that x is a member of asymmetric difference B. Is logically equivalent to x is a member of B symmetric difference A. Therefore, by the definition of set equality, we may conclude that asymmetric difference B equals B symmetric difference A. And that ends the proof. The key to this proof is remembering, first of all, from foundations, set theoretic identities should always be proven with truth tables. And second of all, to understand that the symmetric difference operation is analogous to the exclusive OR. You are looking for either x to be an A or B, but not both, which means you're looking for exactly one of the entries in these two columns to be true. Okay, we have now proven that symmetric difference is commutative, and in the next video, we will prove that symmetric difference is associative. More to follow.